Swayam Prabha. Digital India. Educated India.
So, I will let's get to this one by one. So, a function f. So, first what is a convex function? We have seen what a convex set is. So, what is a convex function? So, a convex function is a function f, let us say from Rn to R, okay, such that f of lambda x, let me use alpha x plus 1 minus alpha y is less than equal to alpha f x plus 1 minus alpha f y, where alpha belongs to 0 1 and for all x comma y in Rn. So, for every pair of vectors x and y, if you look at the convex combination of these vectors with the weight alpha and look at the function value of f at the convex combination, that is less than equal to the convex combination of the values itself. So, you here on the left hand side you have the function value at the convex combination of the points, and on the right hand side you have the convex combination of the function values, right. So, and you have an inequality between the two. So, the left hand side is less than equal to the right hand side. This is what it means for a function f to be convex. Now, if f is, so if you usually if you have, you can actually say more. So, if, so let me write a lemma here. So, let f be C1, then f is convex if and only if, let me write this full, if and only if f of y is greater than equal to f of x plus the gradient of the function at x transpose y minus x. This is true for all y and x. Now, what does this say? What this condition says is, let us visualize this. What this condition says is, so here's suppose my function f. Now, for this since this function to be convex, what it means is that here's suppose a point x, here's suppose a point y. This height here is f of x, this height is f of y, and I take a point like this alpha, I choose an alpha in 0 1. So, I take a point alpha x plus 1 minus alpha y. So, suppose I take this point, right. Now, for this function to be convex, what must be the case is that if I take alpha times fx plus 1 minus alpha times fy, which is if I take the convex combination of the function values, then that must be greater than equal to the function evaluated at the convex combination of the points. So, if I take the convex combination of the function values, then that gives me this height. This is actually alpha fx plus 1 minus alpha fy. And what is this height? This height is simply f evaluated at alpha x plus 1 minus alpha y, right. And sure enough, this function is convex, because as you can see, we have this point here, this value is greater than, this height is greater than this height here. The height alpha fx plus 1 minus alpha fy is greater than the height f of alpha x plus 1 minus alpha y. So, a function like this is this sort of function is convex. Now, what is this second lemma saying? So, for that let me just draw the same function here again. Okay. So, what this lemma is saying is, well, if I, so let me just draw this in a slightly different way. Yeah, what this lemma is saying is, take any point x and another point y. So, here is a point x, here is a point y. Look at fx, that is this. Look at fy, that is this. Now, in addition, look at the gradient of the function at x. So what that means is I am looking at the slope, the tangent drawn to the function at x. Okay. So, it is saying look at the gradient of the function at x, and now extrapolate the function linearly along this gradient. So, if you extrapolate the function linearly along this gradient, so at any point the value of the linear at any point z like this here in between, the linear extrapolation would have value exactly this, the height here, right. So, this height here is nothing but fx plus gradient of the function at x transpose z minus x, right. So, now what is this inequality in the lemma saying? This the inequality in the lemma is saying that you take any point y, okay, you take any point y like this. So, this sort of point y, and look at the value of the linear extrapolation from evaluated at x, or the linear approximation to the function at x evaluated at y. Okay. So, we will take this linear approximation, evaluate that at y, and that linear approximation, its value at y must be less than the value of the function itself at y. It must be less than f of y. So, in this figure f of y is this height, and the value of the linear approximation is actually this. It's this particular. It's negative actually. It's below the axis, right. So, this tells you that f of y is definitely greater than the value of the linear approximation. So, what this means is, what this lemma is effectively saying is that this is true for every x and y. So, which means you can take any point x, draw a linear approximation to the function at that point, take any other point y, look at the function value at that point and look at the value of the linear approximation evaluated at that point, and compare the two. It must be the case that the function value is greater than or equal to the value of the linear approximation. So, geometrically what this means is that if I take the entire linear approximation to the function at any point, then it must be that linear approximation is actually a linear under approximation. So, this linear approximation is necessarily an under approximation, means it always underestimates the value of the function. Means if I wanted to estimate the value of the function using a linear approximation like this, it will always be less than the true value being f of y, right. So, what this lemma is saying is that a function is convex if and only if this holds, means that if a function is convex if and only if the linear approximation to the function lies completely under the function, it under approximates the function, or the other way around also, if the linear approximation of the function underestimates the function, then it has to be that the function is convex. If the linear approximation of the function underestimates the function, linear approximation of the function evaluated at any point underestimates the function, then it has to be that the function is convex. Okay. So, this is what so this is an equivalent you can say characterization of convexity. Some people use this also as a definition of convexity. Of course, it does not hold when the gradient is not when the function is not differentiable, and in that case you will not be able to take the gradient, but for differentiable functions this is equivalent to convexity. All right. Now, what does this give us? So, this gives us the following simple fact. Okay. So, let us look at this. So, I will state this theorem. Maybe I should write this in red because this is an important result. Okay. So, before I go there, actually I should mention, so here is a convex function. Now, what is a convex optimization problem? A convex optimization involves minimizing a function f subject to constraints g I of x less than equal to 0 for all I from 1 to m, and so these are inequality constraints and equality constraints that are linear. So, equality constraints must take the form A x equal to b. Okay. So, here the function f and the function g I, these are all convex. So, if you, it is very easy to see here from this case that this, if you look at the constraints or the feasible region, the x such that g I of x is less than equal to 0 for all I from 1 to m and A x equal to b, this set S is actually a convex set. So, when G I are convex and the equality constraints are all linear, then the feasible region is actually a convex set. So, then what we are doing is effectively minimizing a convex function f over a convex set S, right. Okay. So, that is what happens in a convex optimization. All right. So, now let us look at what happens to KKT conditions for convex optimization. So, theorem, consider a convex optimization. Convex optimization problem, minimize fx subject to gi of x less than equal to 0 for all I from 1 to m and Ax equal to b, okay, where f and gi, these are in C1 and convex. Now, suppose, suppose there exists lambda I greater than equal to 0 and say, so I will, and a theta j, okay. So, the matrix A here, let us suppose the matrix A is in R P cross N, okay. So, there exists a theta in, so let us suppose this theta belongs to R P such that if I take the gradient of the Lagrangian with respect to x evaluated at x star lambda theta, this is equal to 0. Lambda I gi of x star equals 0 and Ax star equals b. So, I have taken the gradient of the Lagrangian with respect to x star with respect to x evaluated at x star lambda and theta. Now, the Lagrangian here will be, just for clarity, let me write the Lagrangian also. So, you have f plus summation lambda I gi of x plus, now the way we wrote it earlier is we took every constraint and multiplied it with its corresponding Lagrange multiplier. The simple thing to do in this case would be to simply do theta transpose Ax minus b. That effectively does the same thing. So, this constraint Ax equal to b can be equivalently written as Ax minus b equal to 0, and once it is written in the form Ax minus b equal to 0, it comes in the form of Hj of x equal to 0 in this sort of form, and then we have to just multiply Hj by theta j. So, what I am effectively doing, that by taking theta transpose Ax minus b. So, that gives me a sum of theta j times the jth row of Ax minus b. All right. Okay. So, this is my Lagrangian for this theta. Okay. Okay. So, yeah. So, suppose there exists a lambda greater than or equal to 0, theta in Rp and an x star in Rn, such that these KKT conditions are satisfied. So, what are the KKT conditions here? Gradient of the Lagrangian is equal with respect to x at x star is equal to 0. Complementary slackness holds between for all constraints, and inequality constraints. Sorry, I forgot. Inequality constraints are all satisfied, and equality constraints are also all satisfied. So, in short, KKT conditions hold. Okay. Then x star is a global minimum of the optimization problem. So, let us take a moment and absorb this. What is this theorem saying? Take any convex optimization problem written as minimize fx subject to gi of x less than or equal to 0, so ax equal to b, where f and gi's are continuously differentiable and convex. And suppose you can find Lagrange multipliers and a feasible point x star such that the gradient of the Lagrangian with respect to x evaluated at x star lambda and theta is equal to 0, lambda I times gi of x star is equal to 0. That means complementary slackness holds and the point x star is feasible. In that case, we must have that x star is a global minimum of the optimization problem. So, notice that I have not said a word about constraint qualifications. It does not matter whether constraint qualifications hold or do not hold. What matters is that you are able to somehow solve the KKT conditions. If you can solve the KKT conditions, the problem, it must be that you have a global minimum. Okay. So, so for that, all you need to do is make sure you have a point that is feasible and you have Lagrange multipliers, appropriate Lagrange multipliers that satisfy complementary slackness and gradient of Lagrangian equal to 0. Once you have that, and you have solved your KKT conditions, you have a global minimum. Okay. This is obviously an extremely powerful result, but it turns out the proof is actually very simple. So, let's quickly do the proof of this. Okay, let's do the proof of this. So, we just wrote that f of x at any point x is greater than equal to f of x star plus gradient of f at x star transpose x minus x star. Okay. So, let x star be as above, and x be any other feasible point. Okay. Then we must have that f of x is greater than equal to f of x star plus gradient of f at x star transpose x minus x star. This is what we just showed, because f is C1 and f is convex, this must be the case. But then what is gradient of f at x star? Well, that can be written through the Lagrangian. The Lagrangian is telling you that the gradient of f at x star, is equal to the negative of, if you look at this here, the gradient of f at x star must be the negative of the sum of Lagrange multipliers times the gradients of the constraints, right. So, just putting that in will now give me that this is equal to f of x star plus summation lambda I gradient of gi at x star I equals 1 to m plus now I need to take the gradient of the equality constraints. So, if you can verify that this actually becomes the same as A transpose into theta. Okay, that's what this becomes. Okay, so this is equal to this what I have written here is just the gradient of f at x star, and I need a negative sign outside this. So, let me put a negative here times, then I have x minus x star. All right. Now, what does this the whole thing transpose? Yeah. Now, let me expand this out. I will, by doing that, I get f of x star minus, now I get sum lambda I equals 1 to m gradient of gi at x star transpose x minus x star plus theta transpose A into x minus x star. Sorry, there should be a minus theta transpose A into x minus x star. Okay. Now, remember x is any other feasible point. So, Ax should therefore be equal to B. X star is feasible. So, therefore, Ax star is also equal to B. So, this term theta transpose A into x minus x star is simply, so this term is actually equal to theta transpose B minus B. So, this is actually equal to 0. Okay, so, this term is equal to 0. So, this term is not present in our problem. Okay, so, we are left with therefore f of x star minus sum from I equal to 1 to m lambda I gradient at x of x star, gradient of gi at evaluated at x star transpose x minus x star. Okay. Now, gradient of gi evaluated at x star transpose x minus x star. Now, this is a similar to the term that we had above here, which came from the convexity of the function f, right. So, now we remember Gi itself is convex. So, consequently, since Gi is convex, so we know that therefore, Gi of x is greater than equal to Gi of x star plus gradient of Gi evaluated at x star transpose x minus x star, right. So, this is true for all x feasible. Since Gi is convex, this must be the case. All right. Now let's look at this term therefore. So, take this gradient of Gi evaluated at x star transpose x minus x star, that is therefore less than equal to Gi of x minus Gi of x star. Okay. So, now what can we say about this difference Gi of x minus Gi of x star? The problem, you can see that all I know is that x star is feasible and Gi of x star is also feasible. So, x star is feasible and x is also feasible. These are the only two things that I know. So, therefore, since both of these points are feasible, what I do know is that Gi of x is less than equal to 0, Gi of x star is also less than equal to 0. But they are both less than equal to 0, that does not mean that the difference is also less than equal to 0 or greater than equal to 0. Nothing can be said about the difference from here, right. So, we need a little bit more information, and that little piece of additional piece of information actually comes from complementary slackness. So, we also have complementary slackness. So far we have used the fact that x star is feasible and that the gradient of the Lagrangian is equal to 0, we will now use complementary slackness. So, complementary slackness, so by complementary slackness, if Gi of x star is less than 0, then the corresponding Lagrange multiplier is equal to 0. So, consequently, if I look at this summation here, this summation actually involves only those lambda i's for which Gi of x star is exactly equal to 0. So, I am going to rewrite this summation now. So, that gives me f of x is greater than equal to f of x star minus some I in A of x star lambda I gradient of Gi at x star transpose x minus x star. Now, A of x star, remember, is those indices, those constraints which are active. Okay. Now go back to go back to this equation here that we wrote out. Let me put this in a box. We wrote this out. Go back to this green boxed equation and look at this equation in the case when x star is actually a point for which Gi of x star is active. So, look at this equation for those constraints that are active, which means Gi of x star must be equal to 0 for such constraints. So, if Gi of x star is equal to 0, then this term actually disappears, then this term disappears, this term is gone. Okay. So, if Gi of x star is equal to 0, this term is gone, and then what I am left with is therefore gradient, okay, for I in A of x star, I have gradient of GI evaluated at x star transpose x minus x star less than equal to GI of x. And what is GI of x? X being feasible ensures that GI of x is less than equal to 0. So, this is indeed less than equal to 0. Now, lambda i's are greater than equal to 0. There is a minus sign outside, and then GI of x star transpose x minus x star is less than equal to 0. What this put together means that f of x is greater than equal to f of x star plus something that is positive, which means that f of x is greater than equal to f of x star. Now, what did we do? We said let x star be as above and x be any other feasible point. It can be any other feasible point, and from there we got that f of x is greater than equal to f of x star. So, x star was my point that satisfied the KKT conditions, x was any other feasible point, and we got that this inequality must hold. So, consequently, it has to be that x star is a global minimum. So, if we are able to verify KKT conditions, we automatically get that that the point that satisfies the KKT conditions is in fact a global minimum of your optimization problem. So, this is how you reverse the implications that have led us to KKT conditions. You use an you work with, if you are working with an optimization problem that is convex, all you need to do is simply check if the KKT conditions hold, and then you get that the point at which the KKT conditions hold is a solution of your optimization problem. Okay. So, with this I will end today's lecture. We can then I will tell you the same fact in a little bit more abstraction next, and I will also tell you about convex optimization, duality in convex optimization in the next lecture. Okay.